Okay, so this next topic is toolkit functions, or sometimes they're called toolkit functions. These are basic functions that are helpful to know. Let's start out with the absolute value functions. When you see absolute value, think V-shape. Typically the absolute value functions that will have a V-shaped graph. It might be a little bit more complicated than that if you have a more complicated expression involving the absolute value, but typically they have a V-shaped graph. The vertex of the V is going to be whatever makes the expression inside the absolute value equal to 0. So this graph here will have a vertex when x is equal to 2. And so to sketch the graph, we want to pick some points on either side of the vertex. So let's say 0, 1, 2, 3, 4. So we have the vertex here, and some points on either side. So if x is 0, we'll have absolute value of 0 minus 2 plus 1. That's going to be 2 plus 1, which is 3. X is 1. We have absolute value of 1 minus 1 plus 1. 1 minus 2 rather plus 1. That's going to be 1 plus 1, which is 2. Absolute value of 2 minus 2 plus 1. 2 minus 2 is 0. Absolute value 0, 0 plus 1 is 1. That's the vertex. Absolute value of 3 minus 2 plus 1. 1 plus 1, which is 2. Absolute value of 4 minus 2 plus 1. 2 plus 1 is 3. Okay, so then we can draw a coordinate system and plot the points. Okay, so have 0 left to right, up 3, 1 to the right up 2, 2 to the right up 1, 3 to the right up 2, 4 to the right up 3, and connect the dots. And it's pieces of two straight lines that meet at the vertex. So that's our graph. Absolute value, V shape. We'll also be working some with piecewise defined functions. If you have a rocket, you'll have a different formula before the fuel runs out than you have after the fuel runs out. I think with the piecewise functions provide some nice illustrations of limits also when we get into so the understanding piecewise functions kind of helps us to understand limits better. Okay, so this function has 3 pieces. We have a straight line type piece and a quadratic parabola type piece. We don't need a lot of points. If we can recognize the shape from these formulas, we don't need a lot of points, but we need probably at least 2 points for each piece. It would be good to have. So I'll say let's say -3 and -2 for the linear part, and then the parabola I'll do -2, -1, 0, and 1, and then for the last linear part I'll do 1 and 2, and I'll put these are actually some of these points are not actually I wanted this one here. We have some boundary points here that are actually not part of the graph, but it's good to do the boundary parts anyway. For one thing, it'll help us to know whether there's a gap in the graph. And so this piece here is going to be for minus x, and this piece here is 1 minus x squared, and this piece on the bottom is x minus 1. And again, minus 2, I put this minus 2 for both formulas because it's on the boundary, but it really only applies to the 1 minus x squared, because for the first formula it applies when x is strictly less than negative 2. Okay, so minus negative 3 is 3, minus the negative 2 is 2, and if we put negative 2 into the second formula, we have 1 minus negative 2 squared is going to be negative 3. And this tells us there's a gap in the graph because these two do not agree. So we know there's a gap here, and we'll do an open circle and a closed circle when we make the graph. 1 minus negative 1 squared is going to be 0. 1 minus 0 squared is 1. 1 minus 1 squared is 0. And this formula here will have 1 minus 1 is 0, so there's no gap here. So that'll be what's called continuous. And we'll talk more about continuous functions a little bit later. And this 2 minus 1 is 1. Okay. This is no gap. I should have put no gap here. No gap. Okay. So then we can draw a coordinate system and connect the dots. Okay, so we have the point 3 to the left down, no, 3 to the left up 3. It's about right here. And then we have the point 2 to the left up 2, except I'm going to put an open circle there because that's not part of the graph. And then 2 to the left down 3. It's about right here. And 1 to the left up or down 0, 0, 1, 1, 0. And I connect the dots here. And then we have 2 to the right up 1 and connect the dots. Okay, so so this shows the gap in the graph, and this will be we'll see some examples like this when we talk about limits. This is in continuity. This function is not continuous because you cannot draw it without lifting your paper from the pencil, your pencil from the paper, because we have a gap here. So you have to lift you draw this part and you lift your pencil and then draw this part down here. So it has a discontinuity here at when x is negative 2. That's where the gap is, and the idea of continuity is related to the idea of limits. We say that the limit as x goes to negative 2 from the left, as x goes to negative 2 to the left, f of x gets closer and closer to positive 2. But as you approach negative 2 from the right, f of x gets closer to negative 3. So the two one-side limits do not agree, and so that there's that's one type of discontinuity where you have the two different one-sided limits, and it's on this other place where you have the change of formulas. The two one-sided limits agree. If you approach from f of x, as x goes to 1 from the right, f of x goes to 0, and as x approaches 1 from the left, f of x also goes to 0. So here this is continuous at this point here, but not at the other point. So this is, we'll see some examples like this to sort of help us understand the idea of limits and also continuity and sort of the connection between the two. Another type of graph is called the greatest integer function. And it's indicated by the double square brackets, and it means the greatest integer less than or equal to x. So that's what it means, greatest integer less than or equal to x. So I'm going to pick some numbers, and it's going to be helpful to pick some fractions and decimals. So I'll say 0, 0.3, 1, 1.7, 2. So the greatest integer less than or equal to 0. Integers are 0, plus or minus 1, plus or minus 2, etc. So this is going to be 0. Greatest integer less than or equal to 0.3 is also 0. But as soon as you get to 1, it jumps up. So it's going to be 0 point anything. The greatest integer less than or equal to 0 point anything is 0. But then when you get to 1, greatest integer less than or equal to 1 is 1. So then it jumps up. Greatest integer less than or equal to 1.7 is 1. Greatest integer less than or equal to 1 point anything is going to be 1. But then when you get to 2, it jumps up. So this is going to be, the graph is going to be, I like to call it a step function or staircase type pattern. Okay, so we have 0, 0, and 0 point anything is 0. So I'm going to put an open circle here, and then as soon as we get to 1, it's going to jump up to 1. And then f of 1 point anything is 1. And I'll put an open circle there. As soon as we get to 2, then the value jumps up to 2. So I think that's enough to see the pattern. It's a staircase type pattern. And you can continue it in both directions. Okay, so that's our function. One application would be the postage rate. At one point it was 50 cents for the first ounce or fraction of an ounce and 21 cents for each additional ounce. So that can be expressed in terms of the greatest integer functions. 50 minus 21 times the greatest integer in 1 minus x, and that applies for x greater than 0. It doesn't make sense for x equals 0 or x equal negative. You can't have a letter weighing a negative amount. And this is another example of a discontinuous function, and the one side limits are different at the integers. So as x approaches 1 from the right, f of x goes to 1. As x approaches 1 from the left, x goes to 0. So the one side limits are different. Reciprocal function. This is actually a hyperbola. We went over some examples of a hyperbola in a previous video, but anyway, we can pick some numbers for x and compute f of x, let's say -2, -1, 0, 1, and 2. I have -1/2, -1, undefined. Can't divide by 0, 1, 1/2. And 2. Okay, so we'll have an asymptote at 0 and also an asymptote at x equals 0 and also at y equals 0. But so we'll have two asymptotes. 2 to the left, down 1/2. 1 to the left down 1, and connect the dots, extend it toward the asymptote. So basically the x-axis and y-axis are the asymptotes. I'm not drawing them because I already have drawn the axes, but the x and y axes are the asymptotes. 1, 1, and 2, a half. Connect the dots and extend it toward the asymptote. So another illustration of limit. As x goes to infinity, f of x goes to 0. If x goes to 0 from the positive side, f of x goes to infinity. As x goes to 0 from the negative side, f of x goes to negative infinity. And just sort of briefly summarize some of the other shapes that you should be able to recognize. Polynomials, degree 0 or 1, those would be straight lines. Degree 2 would be a parabola, there's one hump. Degree 3, you could have up to 2 humps. You have a hilltop and a valley here. The 2 humps. Sometimes the humps flatten out, so I say up to 2 humps. It could be fewer. Degree 4 up to 3 humps, and so forth. Here we have 2 valleys and 1 hilltop. So those are polynomials. We have semi-parabola, square root functions. Would be square root of x is a semi-parabola. Square root of 1 minus x squared is a semicircle. Those are the and generally the square root functions tend to be semi-conics. We could have a semi-hyperbola or a that's basically it. Semi-parabola, semi-hyperbola, semicircle. Exponential and log functions. We'll especially work with base e. Some applications you might have base 2, for example, bacteria doubling every hour. You might express it in terms of the bacteria population equal 2 to the x. But base e has some nice properties. One thing is that for base e, the equation for the slope is the same as the equation for the original function, but we'll say more about that later. But and then the inverse of the exponential function is the log function. Ln stands for log base e, and again it's called the natural logarithm. And these have asymptotes also. The exponential function has a horizontal asymptote y equals 0, and the log function, I'm frozen here. To unfreeze. I think I'm unfrozen now. The log function has a vertical asymptote, x equals 0. And then we have the trig functions. In the previous video, I was looking at trigs from as functions on angles, but there's some applications where it's useful to think of the inputs not so much as angles but as real numbers. For example, a person's blood pressure, when the heart contracts, the pressure goes up, and then in between contractions the pressure goes down. So you get it's kind of a wave function here. This is the graph of sine x, and we can get it by plotting points on the unit circle. If you go to negative pi over 2 on the unit circle, the y coordinate is -1, and if you go to negative pi over 4, angle pi over 4 on the unit circle, the y coordinate is negative root 2 over 2. So we can get these values, look at the unit circle to get these values, but then we're going to plot it on scale it on, instead of we're going to plot it on x versus f of x on a rectangular coordinate system, with the horizontal axis being the input and the vertical axis being the sine. And if we restrict the domain, then we get we can get an inverse. So if we restrict the domain to from minus pi over 2 to pi over 2, then this is the restricted domain here. If we restrict it to this, then we can get an inverse, and this would be the graph of the inverse function. And you can do that for the other trig functions too. This is kind of a quick overview, but cosine inverse is similar. Cosine function is similar, except it's shifted over. It's going to be a wave type function here, and the tangent. Yeah, the tangent looks more like it has some vertical asymptotes with the sine over the cosine. So when the sine is 0, when the cosine is 0, you're going to get a vertical asymptote there. So the cosine function is going to look something like this, with well, it'll look something like this here. The tangent. This is a tangent function. So you'll have two vertical asymptotes, and it's also periodic. So it's going to repeat. The pattern's going to repeat. So anyway, but that's sort of a very quick review of some of the toolkit functions, and that concludes this presentation.